going to have a thinner crowd today. We don't have the live streaming.
No.
Your slide, though. There are weird gray boxes where there must be messages or something over your slides. Went away.
How's that?
That's fine. Thanks. You have a gray box there.
Your video. I don't know if I can.
Yeah, I say that it's WebEx. Something about WebEx.
Oh, are you all right?
And the sound is pretty good, but it would have been better if you had a headset or a, phone. But it's pretty good.
Don't forget when you get on the road.
All right. Maybe another couple minutes to assemble and then just get started. The slides that you sent me like yesterday, can I go ahead and post them?
Well, they're a little updated, I think. I'm pretty sure I updated them. Yeah, I'll send you a set.
Yeah.
After.
Yes. Okay, so who's on remotely, I'm going to mute you. So if you have a question at some point, and you can either raise your hand or ask a question, but you'll need to unmute yourself. Okay, let's go ahead and get started. We're continuing the JWST Community Lecture Series, and today we're very lucky to have Karl Gordon. He's going to tell us about the JWST Absolute Flux Calibration program. So Karl, take it away.
A program that's been ongoing for a little while, but also still in progress, and so I'm always interested to hear what other people's thoughts are and if there are suggestions for improvement. Okay, and so what are the goals of calibration for JWST? This is to ensure high accuracy, relative, and absolute flux calibration for all the instruments. Not only just do flux calibration, we do need fluxes that are calibrated well enough, usually 5 or 10%, but in order to get the most of the observations, we really want to get as high accuracy as possible, and this is, looking at standing stellar physics all the way to dark energy measurements. We're going to do this using a sample of stars with known fluxes that cover the JWST wavelength range. How accurate do we need to be? How accurate do we need to know the fluxes of these stars in order to meet our goals? Nominally, the requirement is 2% absolute accuracy, but we'd like to go as high as is reasonably possible. There are science cases that 1% better could benefit from, dark being the one that is usually the most obvious. With heritage, we'd like to be able to do cross-calibration with Hubble, Spitzer, ground-based telescopes, etc. We live in an era of multi-wavelength astronomy, and also there's a lot of synergies between these telescopes that, at least I expect, JWST will take advantage of. So when I say flux calibration, in this case, the knowledge conversion between dN per second and the physical units, like is one, the IR one, ergs per centimeter squared per second per angstrom. A possible range of fluxes. We really do need sources with known fluxes at wavelengths of interest. Basically, measure the dN per second with your instrument, divide the known flux by dN per second. That's your calibration factor. That's what you multiply all your data in dN per second by to get physical units. So we do need sources with known fluxes, reference standards. There are a few. The ideal ones are ones that are directly to laboratory calibrated black bodies. Everything from NIST standards to, in the olden days, it was more the melting point of copper or so on. These usually are stars like Vega or Sirius, very, very bright stars. But there's also a set of sources from a mid-course space experiment that I'll talk about a bit later that are very interesting. They were measured in space with NIST sources. Then that's the kind of the standard and how you transfer it from a laboratory measurement into the astronomical sky. These are extremely bright and not that many of them, and so then you establish secondary sources which are measured via relative measurements to the standards the above standards, the ones where we've measured them against laboratory black bodies. And in general, you don't usually have those measurements at all wavelengths. You have them at specific wavelengths. So then we use models to interpolate and extrapolate to the wavelengths of interest. Basically, the models are usually physical models, using our knowledge of physics to do this interpolation extrapolation, that is drawing lines. I'm going to use the word flux and as the same thing as flux density. In the physics land, I believe it's irradiance or spectral irradiance. Flux is the shorthand for all of those quantities when I talk about flux calibration. I want to talk about, just to give kind of a historical view of what's been done with a couple of space telescopes. To give the shoulders we're standing on, right? We always stand on the shoulders of the pre-work. In particular, I'll pick out the Hubble Space Telescope and the Spitzer Space Telescope as the telescopes that really JWST overlaps the strongest with. And so calibration is based on 3 white dwarfs, and there are the phone numbers for them. And STS and NICMOS or WIPC3 spectroscopy. That's the observations that are done, and then there are custom non-LTE model atmospheres of these dwarfs. Dwarfs are picked because they're thought to be some of the simpler ones to model, especially 2 of these are only hydrogen white dwarfs, and so you just have to understand hydrogen to model them. The stellar atmosphere parameters like log G and T effective and metallicity, well, in this case, not much metallicity, are fitted using optical Balmer line profiles, which are taken from ground-based high-resolution spectroscopy. And how those Balmer line profiles are broadened is measurements, and the depth of them are measurements of both the effective temperature of the star as well as the gradient. View that Ruppel and myself and Grant Tremblay wrote about kind of all of what led up to the Hubble being based on just these 3 white dwarfs, and kind of a history of UV and optical and near-infrared calibration of the last 20 or 30 years. Well, the Hubble calibration has been checked versus A and G type stars and found to be, this white dwarf calibration is consistent. So just to show how well this can be done, these are the residuals for the 3 white dwarfs. These are the primary HST standards. And that just means it's the observation divided by the model over a broad range from the UV all the way to 1 micron. And you can see that the accuracy is quite high, 1% or less residuals between these 3 white dwarfs. And so this is indicating that achieving a very high accuracy is possible for absolute flux calibration. Hubble very well. And so other things that Hubble has done that's somewhat unique is, so those are the measurements of the 3 white dwarfs. Well, how do you then transfer those measurements? We still have to transfer those measurements to something like Vega or Sirius, which has been measured on the ground against these laboratory black bodies. And the ideal way, and what Hubble has been able to do, is actually to measure it by actually measuring Hubble and Sirius directly with this instrument, in this case STS, the Telescope Imaging Spectrograph. And this Detect on these are somewhat nice in the fact that while you may fill up a pixel in the detail, the charge just bleeds into the next pixels along the same column and wavelength, and so you actually can just add up a wider region and you can get the total flux even for sources that are extremely bright. In this case, Vega and Sirius, which you can see are 0 or even negative magnitudes. About this is that this provides a direct link and a direct transfer between the laboratory black bodies and the main white dwarfs, which are the calibrators. And all we rely on here is that STS is a linear detector, which is where this transfer has been done. It's not Vegas haven't been measured at all with links, but usually it's done in not the V, but at 5556 angstroms. This is this point here at about 0.55 microns. The point, I guess I can point. There we go. I can point that point there. It has MSX points, and so this was an experiment that was done. They did a very similar measurement, but in space, in the mid-infrared, directly against little spheres that were ejected from the spacecraft that had been calibrated by NIST and therefore observed the same way that the observations were taken of Sirius and Vega. And so this is very nice. Hubble is now based on very easily traceable back to laboratory black bodies and very dynamic range with Hubble. As a result, very nice the incredible dynamic range that Hubble STS provides is what is actually enables kind of direct calibration. Move over to Spitzer. Spitzer's that's the other half of the wavelength range that maybe Hubble, that JWST is going to cover. And how was Spitzer calibrated? Well, Spitzer calibrated there's 3 instruments, IRAC, IRS, and MIPS, all calibrated with slightly different programs. For IRAC, K giants were used. Interestingly, originally only A dwarfs were used, partially because the templates for the K giants weren't consistent to be A dwarfs, and there is good reasons to believe that A dwarfs are easier to understand and easier to model from a sub-atmosphere point of view than K giants, which have secular bands that I'll show in a moment. The answer here was 2% accuracy and 0.5% repeatability. So there's the difference between accuracy and repeatability. Accuracy means that's how well you can translate things directly to flux units, whereas repeatability is if I go back to the same source over and over again, how repeatable am I in the native units of the detector, dN per second, for example. The repeat kind of gives you a floor how accurate you can be, because there's that's telling you what the systematics and noise in the detectors are that limit your absolute calibration in the end. And these measurements are usually taken well in excess of a signal noise that would be much lower than 0.5 cents. So we know that it's systematics and it's not signal noise, not just photon statistics. It was challenging because the SF was undersampled for IRAC, and they found that you could actually see the difference of exactly where in a sub-pixel the source fell and how much correction was, how much different it was depending on where it fell. And that little plot here shows, especially these two in the lower left-hand corner, pixel phase. So this is inside a pixel, and the bar here is about -% to +0.5%. And you see that it really changed by an order of 10%. I got this right. Yep, 10%, depending on where exactly in the pixel you fell. And so this is the responsivity varying across the pixel face itself. But they were able to measure that and calibrate that out. And so that actually allowed them to get this level of accuracy. And I've listed the 3 papers that really go through and give you all the details of the calibration. And on that for many things. Oh, someone raise a hand. Yes? You might have it yourself, Jennifer.
Sorry. Apologies.
No worries.
It was an accident, sorry.
Oh, you didn't have a question. Well, it's nice when there's someone asking a question, so don't worry. Anyone, feel free to ask questions, anyone. Interaction is more fun. All right. So that's back. Not quite as accurate as Hubble in a sense, as STS has been able to, but pretty close. Maybe modulo this undersampling, which we should think about for JWST, because not all wavelengths in JWST are going to be fully sampled. By sampling, I mean pixels full width at max, say in the point spread function for the imagers. Okay, how about the infrared spectrograph? This again, K-giants and A-dwarfs, very similar. K-giants have an issue, which is a variable SIO absorption band at 8 microns. That's particularly hard to model, and in fact, the RS observation shown that it's not, that it is challenging. It's not as easy to predict even with more information. And this is shown here in this upper plot for the K-giant, where you see a synthetic spectrum from a model in green, and then in purple there's a spectral template. So a lot of times, if you can't model it with a stellar atmosphere, maybe you can make a template based on other observations, and that template you might use. And where that is the actual blue co-added spectrum. A-dwarf, of course, be challenging, especially further into the mid-infrared debris disks, and so you start to see an X above the stellar atmosphere due to the dust in debris disks radiating. So the calibrated strategy that IRS ended up using is the A-dwarfs were modeled with stellar atmospheres, which in the lower panel here, you can see they did a good job of reducing the observations, especially for delta UMI. Used that as their primary and then calibrated the K-giants and then added the K-giants into this as they were much more numerous across the sky than the A-dwarfs. This is one of the reasons why K-giants have been used in the mid-infrared for some time. The telescopes and instruments didn't have the sensitivity to go very faint, so they needed sources that were brighter. JWST will be able to go fainter, and so maybe that'll allow us to relax that restriction, and we can go to easier to model stars. And this is in a paper by Sloan et al. So what about the multiband imaging photometer for Spitzer? This is what I worked on, so of course I know more about it. I think this is really based on A stars. In parentheses, I show the accuracy. 24 microns, it was A stars alone, and that gave 2%. At longer wavelengths, it expanded out to use many more stars. 5%, there was a little spectral energy distribution mode that gave 10%. And at 60 microns, a exciting blue required us to move to asteroids. So a set of papers there. So nice, again, we were able to get pretty good accuracy, especially 24 microns, which is the best overlap with JWST. I just highlight a couple of things out of the 24 microns. The repeatability was quite good, 0.3%, which for the longer wavelengths of JWST, which are based on similar array technology. You can see that in this plot here on the left. And that's 1%, and that's 1% down, 1% up. That's nice and tight. And then also another thing that Spitzer did that was careful to do is make sure that we were linear over a broad flux range. And this is to show that you have linearity, right? That you're actually linear. Yours are linear. Your flux calibration is the same both at bright fluxes and faint fluxes. And so from that, there are other calibration. There's ground-based calibration that's been done. There's other space-based telescopes like WISE and Akari and MSX. And so if you kind of take all that together and put it together, what would be an calibration program? And this is something I got to think about is when I started on JWST a few years ago. We're far enough from launch. If you had the time, what would you come up with? And so we did, and we came up with this set of criteria. So we really want a statistical sample of sources. So really lots of contaminants. Buying debris disks. Stars are just hard to model for whatever reason. So we want to have enough that we observe that you can identify the outliers and remove them from your calibration sample. Of course, you want to do as much as you can before you observe that your expensive space telescope. But your new telescope will have better capabilities than you've had in the past, so it still may reveal some sources that are not ideal for calibration. This illustrates one of the things about calibration, which is that the ideal calibration source is the most boring star or object that you can find, i.e. one that you really do understand very well from physics. You can model it well. You're not going to really learn new physics or new astronomy from these sources. They really are as boring as possible. So these sources with known spectra, so we have good physical models or templates. We'd like kinds of sources so we're robust to modeling systematics, right? So if we only get A dwarfs, maybe there's some systematic error in the stellar atmospheres of A dwarfs. We would know it, and unless we found some other kind of source that maybe had a different systematic or maybe didn't have the systematic. We'd like a range of fluxes, so we can ensure that calibration applies to all observations, not just the bright observations. Usually calibration stars are bright because you want very high signal and noise, so you're not photon dominated. We'd like to have at least one or more stars often. We'd really like to, this is the measurement of repeatability, so you can measure the intrinsic limit of the calibration, limited by something about the telescope detector combination. There will be a fundamental limit to the signal and noise we can achieve. We'd really unify program across all instruments. This has kind of been done on Hubble. It really wasn't done on Spitzer. There were similar programs and they were cross-checked, but the accuracy of the relative calibration is in general not as high as it would be you could do if you just had the same set of sources. We definitely have to provide direct ties to previous missions and surveys so that we can make those multi-wavelength observations and investigations possible. So now more in detail about the absolute flux calibration plan for JWST, but I want to point out this is not me. There's actually a large group of people who've been working on this. This is, of course, we're a NASA thing, so we have to have a working group. This is the JWST Absolute Flux Working Group. It leads the effort for all instruments, and so this is one of the nice things getting early we were able to do. Is we're able to do it all as one unified program and not have separate programs by instrument. And the JWST instrument teams have this, and I think it makes sense. It's very practical. Worked on this around 2008. Where we really define the plan, calibration targets, do the predictions for the targets, and lay the absolute flux associated quantities. That's what this working group does. I've listed the numbers there. Myself, Bolin, kind of lead the effort and been working on it the longest. We've had more people join, and there's lots of expertise both in the field of absolute flux calibration as well as the JWST instruments. All right, so we're going to do this uniform calibration across all 4 instruments. We picked a sample of 3 different kinds of stars. They're hot stars, and by hot stars I mean OB stars and white dwarfs, A stars and G stars. And we want the sample to cover the sensitivity range of all the JWST instruments, and with at least 5 of each type observable with each filter and grading. And the idea of this is work that Rob Bolin has done on Hubble has shown that you probably can predict the fluxes of stars to about 2%. And for that you work, there's just weather in the stars. There's most stars exactly the same, right? And each star has slight differences, and so there's going to be some noise around the model predictions. At about 2% seems to be the number. If 4 stars, then that should be able to average them and get hopefully 1%, at least to start with. And that's 4. 5 is, we're going to assume that even though we're working very hard to select a sample, there probably will be at least 1 outlier in each of these bins, and so we'll be able to throw out 1 and still have 4. Do relative predictions for each star. This is stellar atmosphere models fit to the observations of each star. And our goal is, we haven't achieved it yet, is to get the effective temperature, gravity, and metallicity determined from profile fit of Balmer lines from ground-based optical spectroscopy, just like done for the white dwarfs. Get the flux levels, set these by measurements of stars at selected wavelengths that are directly tied. As I've said, think of Vega Sirius. There's also a program called Access and MSX targets. And I think I have somewhere more about this Access rocket a bit later. We'd like to have at least 2 such of these absolute measurements that separate widely separated wavelengths, like V at 8 micron or K at 8 micron, so that we only tie the absolute level, but we also tie the relative shape as best we can. We're going to try to, we'll do a full statistical treatment of the flux calibration to provide both the calibration and uncertainties, including the covariance matrix, i.e. how the flux calibration at wavelength 1 depends on the flux calibration at wavelength 2, to allow you to actually take that into account when doing statistical analysis of JWST observations. One star sample. In a single star is sufficient, but right, if you had one star you knew really well, that's all you'd have to observe. I've already started to say why that's maybe not going to happen, but just to emphasize that, you know, no star's flux is really known to perfect accuracy. And there's been unforeseen properties of potential such stars that really really caught us out in the past. And Vega is the post child for this. This was a star that everyone picked. It was zero magnitude. It was an A0 star. It was a straightforward model. And the nice thing was, okay, so we've got this very bright star. Everyone can tie to it. But it turned out not only to it has at least two flaws. One is it's a rapid rotator. So it's actually rotating so fast that the effective temperature of the pole and the equator differ by, I think, 1,000 or 2,000 Kelvin. Okay, quite significant. And that it's pole on. So we didn't know it was a rapid rotator. Just complex. And then in addition, it has a debris disk. Debris disk in the infrared. So it's not even a very good star. So it's been used a great deal in the past. And so it's known for years it's not not a star. But it illustrates why you don't want to pick just one. So we're looking for a sample of stars with known fluxes. Here's the results. I already said 2%, 1% goal. Excellent. All right, all that. Excellent. One last thing. The types were picked really to have high accuracy stellar atmosphere models. Can we model these stars? Is there a good track record of modeling them? So hotter stars, the A's and the OBs and the white dwarfs, we have pretty good stellar atmosphere models. And we pick stars because our sun we've known our sun a long time. There's lots of observations of our sun. So not only have really good observations of it, we also maybe have a deeper understanding of solar type stars, because we don't just get the total flux, but we get resolved measurements, etc. Our models to do this interpolation extrapolation. So, for example, how did we pick it? We wanted stars with heritage. So things like, we definitely want to do the white dwarfs that are used for Hubble. OB stars were used for the International Ultraviolet Explorer calibrator. These are not only straightforward to model, but they also have their primary Spitzer IRAC calibrators, as well as some of the A stars that we'll be able to use also were for IRS as well. And G stars, these are solar analogs, so we scan them. We also wanted to include the NICMOS primary calibrator. This is an JWST source. And any stars that were proposed by other JWST efforts. There have been smaller efforts as part of particular instrument teams. So we did want to be quantitative, not just say we're going to get enough stars. We want to cover the instrument sensitivities, and we define the instrument sensitivities as the maximum flux you can get is saturation in the smallest array allowed. The minimum flux for imaging is a signal noise of 200 in 1 hour, maybe the longest you might think about iterating on a source for calibration. And the minimum flux for spectroscopy was more like a signal noise of 50 in 1 hour per resolution element. And that's on what we maybe do, what's reasonable to do for from the Hubble STScI calibration. Sam, there's a couple of reports that have written the sample up. We can provide them. But of course, this talk itself and the slides provide the sample, the current sample as we've defined it. These are the hot stars. I'm not going to go through them. I just put them up here for reference. A stars. And there's P3E is the NICMOS primary standard, so we've got some of the one good heritage. And finally, so now we picked our sample. Now, how are we going to predict the fluxes? Well, they're not fitting stellar atmospheres to the HST STS and NICMOS WFC3 spectroscopy. This is really very synergy and nice thing that the Hubble director has made available is say, okay, JWST is important. Let's make sure we get Hubble observations of all of the stars in the JWST calibration sample. And so we have a STScI from as short a wavelength as reasonable, 0.1 microns all the way out to 1 micron. And that's really, so now we have really good spectrophotometry over that range. Some of them we've managed to extend longer with WFC3 or NICMOS. Well, at this point, what we do is we fit stellar levels, either Marks or Cruise, which is the new, which is a new Cruise model grid. And fitting, you actually, right now we're using this fitting to determine the effective temperature log G metallicity from the broadband SED, from the HSSED. We don't have the ground-based optical spectroscopy yet. We've got a pretty good constraint on it, and this shows the importance, this particular plot here shows the importance of including the near-infrared in the model fitting. The green is if you don't include the near-infrared, and you can see that it's off by a few percent. The near-infrared and mid-infrared in particular are useful in constraining the models, and I'll say how we're getting more data in that wavelength range to help turn these model predictions from just extrapolations over a large part of the JWST range into interpolations, i.e. if you can tie it at longer wavelengths. So, just show some of the representative predicted spectra, even from the FIT, extrapolation beyond 2.5 microns. And here there's a nice way, if you start working in the near and mid-infrared for looking at stars, if you multiply them by lambda to the fourth, if it's in ergs, this ergs units, or lambda squared if it's in Janskis, you get a pretty flat spectrum. Otherwise, the spectra would be extremely steep, and you wouldn't be able to see many details. So, nice way to look at it. So this kind of shows in red the G stars, in green the A stars, and in blue the hot stars. For just a few here, there's more. And so what we ended with this is put these with the sensitivities. And so here this shows near cam. This shows the imaging filters, the wide filters for near cam, with their sensitivities by these bars. There's max, and then in. So that's the range over which we think we can get good fluxes with high enough signal noise. And in the annual, there's a little tick mark somewhere in between, and that was the transition between using subarrays above that tick mark and full frame, the full array below it. So first off, you can see it. All right, so higher end, we're well covered. We've got a lot of sources. We've probably got our 5 sources. But it's a lot, and so this is a good way to diagnose, do we need more standards? And the answer is yes, we do need more standards at the faint levels to make sure, one, we can well calibrate the full as well as subarrays, and no systematics between those two, but also we can check for nonlinearities at the lower flux levels. But I'll talk about a program in a little bit that's working on getting fainter calibrators so that we can fill in that range. It's pretty good. Near cam, this is for the medium and narrow filters. Better for these, especially the narrow filters. Of course, the sensitivity of the narrow filters moves up because they're narrow filters, so they don't get as many photons in the same observation time. Those are all covered. We could use a bit more bit sources at the fade-in for the medium band filters. Do the same thing to make that check to make sure everything works. But the near spec actually is pretty good shape. It's good coverage for both bright and faint fluxes. As you see here, for resolution 100 all the way up to resolution 2700. That's the wavelength range. The spectral resolution range of near spec. So near spec good. We're good for near spec. Spectroscopy. This is pretty good coverage for SOSS. This is the single object slitless spectroscopy mode. These two here. But for wide field slitless, again, just like near cam imaging, we're missing source at the fainter end. So we now have 2 instruments that need sources at the faint end. Imaging is similar. It's not meant to be a regularly used mode. It's a similar imaging, similar kind of detector as the NearCam imager. So it has the same issue. Feiner says we need more Feiner sources. How about so mirroring? This is an infrared instrument. It's got pretty good coverage in all the bands. Although the challenge for mirroring is that, especially as you go to longer wavelengths, the sensitivity is not as good. And so we actually could use some bright stars to fill things in at the longer wavelengths. And in here is, this plot actually shows Vega for reference. This is not real Vega, this is a model for Vega that's just the stellar atmosphere. That at the longer wavelengths, extremely bright sources, which we take advantage of. I'll talk more about that in a moment. Very Carthy and spectroscopy. It's pretty good bridge. Again, for the medium resolution spectrometer, which is about 3,000 resolution, we definitely need brighter stars to fill in the high end. Bright stars are easier to find than fainter stars in Flux calibration work. That tells you what our current plan is. We are still 2 years from launch. We'll have ideas on how we'd like to really and make the sample even more robust, make the prediction more robust. So what are we doing right now? The in-progress or planned work. We want to sample to both fainter and brighter stars, obtain the ground-based optical high-resolution observation, so we have another way of getting the stellar atmosphere parameters. We'd like to make sure we complete the Hubble and Spitzer observations, motivate port updated stellar atmosphere grids, improve the from primary to secondary standards. This is this transfer of things that have been measured directly on laboratory black bodies against laboratory black bodies to the standards that we can observe more often when we build instruments, and then update our sample not just to most of the I showed you showing the sensitivity ranges are based on a couple years ago, and now we have the instruments they're built. We've better understanding their sensitivity and saturation. We just update things to make sure that things haven't changed significantly. There's no indication they have, just sure. So a little on those points. So how sending the sample to fainter stars? This is an effort led by Everett. I probably get his name right. On the NearCam team, the challenge here is how do you find, say, G-type stars? You want to find fainter G-type stars that are 17th magnitude. Well, that's not necessarily, you don't just look those up. And so very cleverly what they're doing on the NearCam team is to pick candidate G-type stars from clusters from their magnitude diagrams, and then get optical spectroscopy to actually do the spectral classification, confirm the candidates. Right? You pick the candidates in the CME from where you expect there to be G-type stars. Then you go get spectroscopy and then use the lines as known stars with known spectral types to actually classify them and know that what kind of stars they are. And then that makes a good candidate star for Calibrated. So that's going on now, and in a couple of months, I've read that we'll have a new set of samples, and we'll add them in to the JWST sample. So the brighter stars is something we've talked about. We haven't actually started doing this yet, but this should be pretty straightforward. We kind of need this for the MRS spectroscopy and long wavelength imaging. We could use that were observed by Spitzer IRS. That's one candidate. Another one is MSX, this mid-course space experiment, and that's because it's a really direct tie to these prime calibrators. And so I want to mention a bit more here. Here's the mid-course space experiment. This was an experiment that was flown by the Air Force to map the galactic plane and some other places, and they spent a significant amount of time on calibration. Those are the lengths where they had bands. And the interesting thing about MSX is it didn't just go up into space and measure it. It actually had little spheres that had been calibrated by NIST. They released them during the mission. I think there were 4. And as they were released and they moved from the shadow into the, they were shadowed when they went out by the experiment. And as they went out and hit the sun and the upwelling Earth radiation, they started heating up and emitting like a black body. And as they had been well calibrated on the ground and they understood the material and how they actually warmed up, you had a calibration you could tie to that was not another star. You actually tied to something you'd measured in the lab. And as the source was flying from the spacecraft, you observed it like a star. That's kind of unique. We're not going to do that on JWST. We're not releasing anything. We don't have any of these things on JWST. But show their accuracy was good to 1.4% absolute, and they had stars that they directly calibrated with many, many measurements over the mission. So these make primary calibrators, not just secondary calibrators. HST white dwarfs are secondary calibrators because they're not directly tied to our measurement. Stars, they're very bright, usually challenging to get, but maybe it's with the medium resolution spectrograph, we can observe things that are this bright, providing direct transfer as long as the mirror detector is linear in infrared to the JWST calibrator sample. So that would complement the HST STS direct transfer. We'd be able to do it with Mary for JWST. All right. Also doing doing some observations on the ground to get the stellar atmosphere parameters. This is just getting resolution 20,000, from 4.7 microns, SPECT, and then you can fit lines, as I said earlier. And so there's a proposal in. This is led by Stacy Bright. It's a proposal in that was submitted to Gemini for the Grace's instrument. We can get the time, and we'll do other proposals as well. And these measurements will complement and tell us something about the systematics of measuring log G and T effective, both from optical, maybe high resolution spectroscopy, as well as from the overall SED shape from the Hubble STS observations. To complete the Hubble and Spitzer observations, all the current sample has HST STS spectroscopy below 1 micron. If we expand the sample, we'll want to add those in and get this spectroscopy for all the sources that are bright enough. Maybe we will then move to filter photometry with other instruments on Hubble if they're fainter, which may very well be. All number of the stars already have HST WST3 spectrophotometry from 1 to 1.7, and WST3 observations led by Susanna Duchesta. And we're to, of course, get the rest of the sample. Getting that the near infrared has been very valuable in constraining the models. In addition, the sample has full IRAC and MIPS 24 micron data taken during Spitzer's cryogenic mission. The cryogenic gone on Spitzer, we can still get data, and that's to get data with the 2 shorter IRAC wavelengths that are still active during the warm mission, 3.4 and 4.5 microns, and this is a collaboration on Karl at the Spitzer Science Center. So that'll help tie the models down so that we not only tie the models down and get the shapes right and remove some of the freedom there, but also gives us a sure tie to Spitzer observations. So we'll have a very good cross-collaboration between missions. So Ralph Bolin in particular is working with stellar atmosphere modelers to get updated stellar atmosphere grids. Not only are these updated to include newer opacities, but also to get better wavelength coverage in the near and mid-infrared. Most of the grids of stellar atmosphere models, which we use as part of predicting the flux brightness at JWST wavelength range, have very wavelength points, the existing grids in the near and mid-infrared, and then stop, say, at 20 microns, and we need them out to at least 28.5. This is working with a couple of bulks. For the LT grid, this is based on Atlas 9, and there's a paper in preparation on that. And Ralph will be beginning discussions on non-LT grids for the hotter stars with T Lustia. So we're really, trying to get the prediction part of it really tuned up as well. Transfer of bright to faint. These stars are calibrated, so ground-based MSX. Transfer of linear detector. So as I said, usually the white dwarfs are a nice transfer. WST STS is particularly nice because it was able to observe Vega and Sirius as well as all the JWST calibrators. But that only overlaps the shortest part of the JWST wavelength range. It would be nice to have it at longer wavelengths. So So use 2-mass and Ys to do this transfer, right? These are longer wavelengths. As long as they're here, we can make this transfer. The under integration looks promising. Another one that's quite promising is this Access rocket. Beth Kaiser is PI on, and this is to take 0.5 to 1.7 micron resolution, 500, 1% accuracy spectra of 4 stars. Big and Sirius are always brought up, but also a couple of 9th magnitude stars, potential ones that are even in the JWST calibrator sample. We are, you know, some of our people on the working group are collaborators or co-Is on that team. And then this rocket is going to be a direct comparison between NIST black bodies and observations. The rocket starts on the ground, they can make the measurements, and they can do it again on the ground, and they're going to use a detector that's well calibrated. We're up, as I said. We've got HST stis and observations, and account that in this CalSpec database, which provides the JWST predictions are all in there already. We have a few from our original sample in those 2 reports. So once update, there'll be a new report with a new sample. Some of them we revealed to be binaries based on HST measurements, or exoplanets, you know, found out since we put them in the sample. Added G stars for the NIRCam work. Added in brighter stars for MIRI, and as I said earlier, update the sensitivities for the ASBEL instruments. And then make sure we still have our target of 5 per instrument mode star type. Instrument mode star type is so that for each our 3 kinds of stars, hot, A, and G stars, we'd like to be able to make a 1% measurement, and with 3 different kinds of stars, we should be able to tell if one of them is deviant. If them are deviant, then we have different problems. But hopefully we'll have 2 out of 3 be good, and I kind of expect all 3 will be pretty good. Kind of this idea of using 3 different types of sources to look at systematics. We did kind of a prototype bit of work on this that was published a few years ago, led by Ralph Owen. And this, we took preliminary JWST sample, and then at that time it was just A, G, and white dwarfs. Looked at spectrophotometry, which was obtained from the Spitzer archive or from a Cycle 5 Director's Discretionary Program. Used most to the HST data, and then direct fluxes, and then asked how do the predicted IRAC fluxes compare to the fluxes we measured. And so basically, this is a measurement of how different is the HST calibration from the IRAC calibration. And the answer was that if we, recalibrated IRAC based on the HST predicted fluxes, it was 1 to 2% lower than the official IRAC calibration. That's actually great. That was consistent with the official 2% uncertainties. Interestingly, the white dwarfs were actually deviant, larger than expected, and then the calibration of the A and G stars. Maybe there's something about white dwarfs not being ideal for IR flux calibration. Maybe. So this is an example of one of the figures out of the paper, and you can see on the top is an A star. The measurements are the errors, right? So there's the IRAC measurements, and then that's the Spitzer IRS blue P-cup filter, and that's MIP24. This RP330E, that's one of the classic solar type stars, and here's one of the HST white dwarfs, and you can see that the prediction, which is in the black line, is high, especially at 8 microns, significantly more than you'd expect from the error bars. A lot of other models that maybe do a little bit in the 8 micron, but maybe they don't do as well as the shorter wavelength. So a red flag, a caution that maybe white dwarfs aren't ideal for infrared calibration. Although some updated non-LT models show a smaller offset. This illustrates the importance of having the 3 different types of stars so that we can tell when we have systematic problems. And so that's it. If you're interested, we're a pretty open group. You talk to myself or Ralph Bowen or anyone on the working group. We're particularly, we're looking for people who are interested in doing model atmosphere calculations, the ground-based high-resolution spectroscopy. One thing I haven't talked about, monitor stars for variability. We don't want variable stars in this. and we're open to suggestions for improvement on the sample, control of schematic uncertainties, or any topic in particular. Thank you very much.
Does Eric have a question? On the chat window. He says he has a mic issue, so he wants to ask via text. So I think that's great, Eric, if you could just type in, oh, here it is. Can you, on the chat window, Karl, Eric's question?
Yep. Hold on just a second. I need to make it clear.
Read it out or something.
I'll just so everyone can hear it. I'm a bit confused on how the stellar model assumptions map onto the calibration. That is, if the models are wrong in some sort of systematic way, how will that throw off the absolute answer? How wrong they have to be for you to do better using a literal interpolation, at least for those that have direct lab comparisons transferred to JWST accessible sources? Let's see. So it's a systematic error in the models. It's very hard to predict how it will be, but for example, if you're thinking about doing stellar atmospheres of a very hot star, maybe you haven't thought about the numerics of what the mid-infrared SED of that star might look like, because it's got so little energy in the mid-infrared that there may be something in your assumptions and when you model the star that will not affect the bulk of the energy coming out of the star, nor the spectrum where hot stars in general are interested for science, usually UV, optical, but might affect us in the mid-infrared. And so you could imagine a numeric going on there, or maybe you decided you didn't need to worry about that series of hydrogen in your model, and you didn't calculate it, even though it's in the mid-infrared range. So that's one kind of systematic in the models that might be important. How it will happen, the impact of that, because it depends on whether it's too high or too low. I think the measure we've already made, we know that there's not huge variations in the there's not huge errors in the stellar atmosphere models. The mid-infrared. That's how bad they would be. I think the stellar atmosphere models are already significantly better than doing a little interpolation between the very few wavelength points that we have, absolutely calibrated. Because usually we have things like measurement in the V band, maybe K band, maybe microns, maybe 20 microns. That's not really not many points. There are a significant number of spectral features in stars in between those. So it's been shown that we have it's much better to use stellar atmospheres to do that interpolation. Even there may be some errors in that, than to just connect the lines. We don't have points to make the lines worthwhile. That answers your question, Eric?
Okay, Jonathan Eisenhammer has his hand up. I'm going to try and unmute Jonathan. Do you want to go ahead with your question?
Yeah, apologies for the possibly a very naive question, but those solar system objects?
Those objects are very intriguing. They've been used a lot, especially in the infrared, but a longer wavelength infrared. Asteroids are the usual object that is. Herschel used them, and MIT at 160 microns used asteroids. Here you need to know something about the rotation, something about the albedo, and the source. They are calibrators that we could consider. Are a bit harder to model because they have a rotation, some rotational issue. They can have some rotational variability, as well as you need to know their albedos. They're also very intriguing because they're redder sources, and so they really have a use understanding, especially when you have broad filters, if you have leaks or is your filter bandpass exactly right. We haven't put them in for JWST because one, a bit harder to model, and JWST has the benefit of being quite sensitive, and so we can use stars, which we think are easier. That is to say, we shouldn't also look at asteroids, and so there are other associated things that I haven't talked about like make sure, we should observe some red sources to make sure that we understand the responsivity of our detectors very well to the different wavelengths. I guess worried about the red part and the need for asteroids. We really just need is a source that is stay red, because there's such good spectroscopy on JWST. I believe we can just take the spectroscopy and then compare it for the filters. So that's kind of, I mean, asteroids are something that always sits there and we think about them, but harder. At least that's my impression. I'm always willing to be told that they're easier than I think. Question?
Yeah, thanks.
Okay.
There's a question from Katie. Lydia? Or, sorry, I'm butchering your name. Could you, I'm going to unmute you, and do you want to go ahead? Yeah. Sorry?
Yeah, it's Lida, like a kaleidoscope.
Oh, awesome. Thank you.
Thanks. I was just wondering what exactly you need for the ground-based monitoring of variability. Can you tell me more about that?
For ground monitoring variability, it could be quite straightforward and just do broadband photometry over, hopefully more than a little period of time. I mean, I guess I expect these sources to be variable. Well, I don't know. I don't know how much these sources have really been checked for variability. I'm going to repeat observations with Hubble, although some of them do. So for variability, I mean, I would be interested in variability, on night time scale to weeks to months to, year time scale, to know if there is some intrinsic variability in sources that will limit the accuracy which we can calibrate.
I feel that could be a really good opportunity for a collaboration with the American Association of Variable Star Observers, or with one of the students, the Space Astronomy Summer Program students. Like that's a project that I've done students in my previous job, where you have them monitor stars, and I mean, an undergraduate can easily run some whatever, Scraggle or whatever they're called, models, yep, and see if there's variability. And if it gets students to a telescope where they get to take hands-on data and help something, or sorry, help JWST with something, then just an idea.
Yeah, it's a good idea. We're right now, some of the limits on what we're doing is we've been able to do is just limits on the amount of time people in this working group have to devote to the projects. So if that's something you or someone else would be interested in leading on, we'd be happy to collaborate and provide help, but not manage the student ourselves at this point. At least that's I can't.
I'd be happy to help after I check with my boss and make sure I'm allowed to do that.
Okay. Just now, if you do, I mean, I think it's a lot of fun, and I think understanding the variability would be a really neat project. I agree. I think it's a straightforward thing. Great.
Does anyone have questions for Karl?
Yes, Andre with Nearest. So, are any of these stars in the James Webb CVC? And if not, plans to add some? No
stars. In fact, the IRAC, especially the IRAC A stars, which are kind of these, I don't know if I find them. And that's one of the nice things about them, especially the ones down here on the bottom with just kind of, 9 digits, or 8 digits, 7 digits, I can't count. 7 digits are all in the CVZ. They're ideal for, we can monitor them all the time. So that's one of the reasons we picked them. So yeah.
Any other questions? Let's thank Karl again for giving such a nice talk today. There will be, I'm going to post a recording of this talk on the JWST page, so everybody should be able to access that. And then I believe Karl is also going to send me his slides. We'll post those as well. So thanks, everybody. The next lecture will be in 2 weeks, and then at that time, Jay Anderson's going to talk about astrometric calibration. Okay, rest of the week.
Bye, everyone.
Bye.